That brief clip showed the operation of a line finder connecting a telephone set to dial tone in actual time. From going off hook to getting dial tone took about 1 second. It's now going to take me 1 hour and 40 minutes to explain it. I'll take the next couple of minutes providing some general line finder information, while the video will be displaying every action of every moving part in the line finder that occurred during that 1 second interval. What you are looking at is a line finder switch. It is one of 3 main types of switches used in step-by-step telephone switching systems, the other 2 being the selector and the connector. The main purpose of the line finder is to hunt for a telephone line that has gone off hook in an attempt to originate a call, and then to connect that line to the dial switch string so that dialing the called number can begin. This is a Western Electric and Bell Labs designed line finder switch that was used extensively in the Bell system. This particular switch was manufactured by Northern Electric in 1965. Its equipment drawing number is ED33013. The ED33013 type switch was first introduced in 1955. Line finders similar to this were used throughout the North American public switch telephone network beginning in 1926 and lasted until the last step-by-step switch was decommissioned in 2002. The line finder has many electromechanical parts that are identical to those found in selectors and connectors. However, its operational functionality is different. Selectors and connectors are called numeric switches because part of their activity is in response to the reception of numeric or dial pulses. They are seized by a preceding circuit and connect that circuit through to a succeeding circuit. The line finder is a non-numeric switch since none of its activity is in response to dial pulses. It functions somewhat in reverse to that of numeric switches, in that it is permanently connected to its succeeding circuit, which is a first selector, and takes action to connect to its preceding circuit, which is a calling line. It should be noted that the mechanical motions you've just seen and will be seeing throughout this video depicts individual switch parts shown in sequential clips. In actual line finder operation, much of this motion occurs in unison. All parts attached to the line finder shaft move in unison. There are a number of parts attached to or directly contacted by the vertical, rotary, or release armatures. All these parts move in unison with their respective armatures. Now I'll provide an overview of all the line finder parts. The 3 main structural parts of the switch are the switch base, the switch cover plate, and the switch frame. The horizontal bottom plate is called the cover plate, which attaches to the switch frame near its front and to the switch base at its rear. It provides support for the test jack assembly and the make busy switch, and acts as the bottom dust and protection cover. The thick gray cast iron switch frame provides the mounting support structure for most of the apparatus on the switch, except for the relays. The vertical rear mounting plate that runs the length of the line finder is called the switch base. The cover plate, the switch frame, and these 6 relays are all attached to the switch base, although they are attached through insulators so that they will not be grounded by the line finder shelf framework. There are 6 relays designated as A, B, C, D, E, and F. We'll be describing their operation in detail when we progress through a dial tone request. For now, I'll provide a brief overview of each of the relay's functions. The A relay, seen here operating and releasing several times, is the first relay to operate upon seizure of a line finder. It provides operating and holding ground paths for other relays and magnets. It operates once on a call and then releases when the connection to the calling line has been established. The B relay only operates on some calls, specifically from line circuits with terminal numbers in the 100 to 199 range, as will be explained later in the video. When operated, it transfers the line finder's line circuit connection capability from line circuits numbered 00 through 99 to line circuits numbered 100 through 199. Once operated, the B relay stays operated for the duration of the call. The C relay manages the vertical and rotary stepping activities. It operates and releases once for each vertical and rotary step taken. When rotary stepping is completed, the C relay releases and remains released for the duration of the call. The D relay operates after the connection to the calling line has been established. It makes the line finder unavailable for selection by other calling requests. It does this by transferring its start chain to the next line finder in the selection sequence. It also opens its branch of the open chain multiple. Details of these terms and activities are provided later in the video. Once operated, it remains operated for the duration of the call. The E relay operates once on each call when it detects that vertical stepping should stop and that the line finder should transfer over to rotary stepping. When rotary stepping is complete, the E relay releases and remains released for the duration of the call. The F relay operates once on each call when the connection to the calling line has been established. It cuts through the tip and ring transmission path between the calling line and the first selector. Once operated, the F relay remains operated for the duration of the call. These two studs are called cover guide studs and are used to help guide this gray dust cover into its seated position when placing it over the line finder. Mounted at the bottom of the line finder switch, there is an arc-shaped apparatus called the bank assembly. The bank assembly is not actually part of the line finder switch, but when a line finder is mounted on its shelf, the bank assembly is bolted to it by these two threaded rods. These threaded rods protrude through the line finder frame and are secured to it by these two nuts. So the line finder and the bank assembly act as one functioning unit. Each bank assembly has 600 of these little metallic contacts called terminals, which are electrically isolated from each other. At the rear of the bank assembly, these 600 contacts are connected to 600 wires, which are cabled over to 200 line circuits. It follows that each line circuit requires a 3-wire connection to the bank assembly. These are the tip and ring transmission path wires and the sleeve control wire. Each bank assembly has 3 tiers: lower, middle, and upper. The lower bank tier contains the tip and ring terminals for line circuits numbered 00 to 99. The middle tier contains the tip and ring line terminals for line circuits numbered 100 to 199. And the upper tier contains the sleeve terminals for all 200 line circuits. Each bank tier has 10 levels of terminals. The levels are numbered from the bottom up, 1 through 9 and 0. Each level has a top and bottom set of contacts, separated by an insulator. On each level, the top side has 10 terminals, and the bottom side also has 10 terminals. In the upper tier, shown here, the top side terminals are the sleeve terminals for line circuits 100 to 199, and the bottom side terminals are the sleeve terminals for line circuits 00 to 99. So in total, the upper tier contains the 200 sleeve terminals for the 200 line circuits. In the middle tier, the top side terminals are the ring transmission terminals, and the bottom side terminals are the tip transmission terminals. These 100 tip and ring sets are associated with line circuits numbered 100 to 199. In the lower bank tier, the top side terminals are the ring transmission terminals, and the bottom side terminals are the tip transmission terminals. These 100 tip and ring sets are associated with line circuits numbered 00 to 99. On every level, the top side and bottom side terminals are given rotary position numbers, which from left to right are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. For any given line circuit, its tip ring and sleeve terminals are always in alignment in terms of their level number and their rotary position number. For example, this diagram shows the numbering of the line circuit terminals on my demonstration unit bank. Let's look at line circuit number 11. Its tip and ring terminals are on the lower tier. Its ring is on the top side of level 1, rotary position 1. Its tip is on the bottom side of level 1, rotary position 1. Its sleeve terminal is on the upper tier and is on the bottom side of level 1, rotary position 1. Now let's look at line circuit 100. Its tip and ring terminals are in the middle tier. Its ring terminal is on the top side of level 0, rotary position 0. Its tip terminal is on the bottom side of level 0, rotary position 0. And its sleeve terminal is on the upper tier on the top side of level 0, rotary position 0. The purpose of the bank assembly is to provide a convenient area for a line finder to achieve connectivity to any of the 200 line circuits terminating on the bank. This is accomplished by means of these 3 wiper assemblies. The lowest wiper assembly can connect to all 100 tip and ring terminals for line circuits 00 to 99, which are on the lower bank tier. The middle wiper assembly can connect to all 100 tip and ring terminals for line circuits 100 to 199, which are on the middle bank tier. The top wiper assembly can connect to all 200 sleeve terminals for line circuits 00 through to 199, which are on the upper bank tier. Each wiper assembly has 2 wipers. In the wiper assembly for the lower bank tier, the top wiper is for the ring terminals and the bottom wiper is for the tip terminals. Similarly, for the middle bank tier, the top wiper is for the ring terminals and the bottom wiper is for the tip terminals. In the upper bank tier, the top wiper is for sleeve terminals for line circuits 100 to 199, and the bottom wiper is for the sleeve terminals of line circuits 00 to 99. We'll come back to the wipers shortly, but first we need to talk about the line finder shaft. The shaft is a 12.5 inch long by 3/16 inch diameter steel rod that is positioned vertically in front of the main parts of the switch. The shaft has a fixed vertical axis, which is constrained by its insertion through 2 vertically aligned stationary bearings. This is the upper bearing, and this is the lower bearing. The shaft can move up and down along its vertical axis, as can be seen here. It can also rotate around its vertical axis, as can be seen here. Notice that there are several items of switch apparatus attached to the shaft. As such, they move up and down with the shaft and rotate with the shaft. The 3 wiper assemblies are attached to the shaft, so they move up and down with the shaft and rotate with the shaft. And here you can see the range of motion of the wipers as the shaft moves up and down and rotates clockwise and anti-clockwise. This motion enables each wiper assembly to wipe or brush across all of the 200 terminals on its bank tier. In my demonstration unit, the line circuit that I am using is on terminal 00. As you can see from the diagram, to access this line circuit, the line finder's shaft will have to step vertically 10 steps and rotate horizontally 10 steps. Let's watch the stepping activity in slow motion. At the end of the vertical and rotary stepping, the line finder is connected to the tip ring and sleeve terminals of line circuit 00. On any call, whenever the vertical and rotary stepping stops, each wiper assembly will be resting on two particular terminals. Here we see the upper wiper resting on the top side terminal of level 0 rotary position 1, and the lower wiper is resting on the bottom side terminal of level 0 rotary position 1. The degree of physical contact between the wipers and the terminals they are resting on is sufficient to enable electrical conductivity between the wipers and the terminals. The wipers are connected to these flexible wiper cords, which pass the wipers' connectivity through to the line finder relay circuitry. So by controlling the vertical and rotary motions of the shaft, a line finder can access and be electrically connected to the tip ring and sleeve terminals of any of the 200 line circuits connected to its bank assembly. Let's turn our attention now to the rest of the apparatus attached to the shaft. Starting at the top is the shaft spring assembly, which has a cap, a coil spring, and a shaft spring bracket. The purpose of this spring assembly is to provide the necessary force to return the shaft to its normal rotary position at the end of a call. The top of the spring is attached to the cap. The cap is fixed to the shaft, and so it rotates with the shaft. The bottom of the spring is attached to the shaft spring bracket. The shaft fits through a hole in the shaft spring bracket, but the bracket is not affixed to the shaft. The bracket simply rests on a clamp, but the clamp itself is affixed to the shaft. So when the shaft steps vertically, the spring assembly moves up with the shaft. Notice that the rear of the shaft spring bracket has another hole that fits over a fixed position post called the normal post. The bracket is not fixed to the normal post and is allowed to move up and down over the post. As the shaft rotates, watch the shaft spring bracket. Notice that the normal post prevents the shaft spring bracket from rotating, and so the bottom of the spring does not rotate either. Let's look at the shaft rotation again. This time we'll focus on the spring cap and the top of the spring. Notice that the cap and the attached top of the spring rotate with the shaft. So, with the bottom of the spring fixed in a non-rotating position and the top of the spring rotating with the shaft, a spring tension builds up as the shaft rotates clockwise. At the end of a call, when the shaft is released from being held in its off-normal position, the spring tension causes the shaft to rotate anti-clockwise to its normal rotary position. The clamp just below the shaft spring bracket is called the normal pin clamp, and clamped tightly in its jaws is the normal pin. The normal pin stops the anti-clockwise rotation of the shaft when it reaches its normal rotary position. It does this by the simple act of striking up against the shaft spring bracket. The normal pin has one other function to perform. When the shaft is in its vertically normal or fully released position, the normal pin rests on top of this pivotable off-normal finger. The weight of the shaft and all of its attached apparatus weighs down the off-normal finger against the tension of these vertical off-normal or VON contact springs. When the shaft steps up vertically by one step, the normal pin is moved up with it and away from the off-normal finger. This frees up the off-normal finger, which can now pivot. This permits the VON springs to operate. Moving downward along the shaft, the next item of apparatus that is fixed to the shaft is the vertical ratchet. The vertical ratchet is one of several devices involved in stepping the shaft vertically upwards. The ratchet has 10 teeth. Each ratchet tooth is associated with a vertical step to a particular bank level. The top tooth is associated with level 1. The one below that is associated with level 2, and so on down to level 9 and finally level 0. Here's a slow motion clip of the ratchet being raised 10 vertical steps. Immediately below the vertical ratchet is the rotary ratchet. The rotary ratchet is one of several devices involved in rotating the shaft horizontally clockwise, one step at a time. The ratchet has teeth which are engaged by a pawl to rotate the ratchet. Each step will move the wipers to an adjacent set of bank terminals. Here's a slow motion clip of the ratchet being rotated 10 horizontal steps. Below the rotary ratchet is this vertically mounted cam called the 11th rotary step cam. This is utilized when there is a trouble condition in which the line finder cannot detect the location of the calling line, or when a CO technician is performing a line finder start chain test. In such cases, the wipers are rotated past the 10th terminal on a bank level to an 11th rotary step position where there are no terminals. These are the 11th rotary step contact springs. They are operated by the cam when the shaft reaches the 11th rotary step. Let's watch. When operated by the cam, these springs will initiate action to release the line finder. Moving further down the shaft to the bank assembly area, we've already talked about the 3 sets of horizontal wipers, but notice that there is an additional single wiper, so mounted that it wipes vertically instead of horizontally. The assembly that has the vertically mounted contacts over which this vertical wiper brushes is called a commutator. The commutator has 11 contacts called segments. The very bottom segment has no circuit significance. It merely acts as a rest stop or guide position for the vertical wiper when the shaft is in its normal released position. The 10 commutator segments above this are associated with the 10 levels of the bank assembly, so they are numbered upwards from 1 through 9 and 0. When the shaft steps vertically upwards, the commutator wiper will rest on a commutator segment number that coincides with the vertical step number. So on the completion of the shaft's first vertical step, the commutator wiper will rest on segment 1. When the shaft has stepped 10 vertical steps, the commutator wiper will rest on segment 0. On each call, one of the commutator segments on the line finder's bank assembly will be grounded to indicate to the line finder that this is the level on which the terminals of the calling line circuit are located. The detection of this ground stops the vertical stepping and starts the rotary stepping. That finishes our discussion of the apparatus attached to the line finder shaft. Let's turn our attention now to the 2 stepping magnets, which are the vertical magnet and the rotary magnet. The vertical magnet is a twin coil assembly. This is the left side coil, and this is the right side coil. The vertical magnet is energized or magnetized each time a vertical step of the shaft is required, and de-energized or demagnetized after each vertical step is completed. It has an armature that is attracted to the 2 coils each time they are energized, and which pivots back to its released position each time the coils are de-energized. Attached to an extension arm of this armature is a vertical pawl. With each attraction of the armature to the vertical magnet, The pawl engages a tooth of the vertical ratchet and forces it upwards by one step. Or, from a different perspective, with each release of the armature away from the vertical magnet, the pawl disengages from the vertical ratchet tooth. So each energizing and de-energizing of the vertical magnet steps up the shaft by one vertical step. Also associated with the vertical magnet is a set of contact springs called the Vertical Interrupter springs. This spring set is operated by a bell crank or L-shaped pivoting lever. Each time the vertical armature is attracted to the vertical magnet, the extension arm of the armature pushes upwards on the lever, causing it to pivot and operate or open up the contact springs. Each time the armature falls back upon de-energizing of the vertical magnet, the lever pivots back to its normal position, releasing or closing the interrupter contact springs. So the vertical interrupter springs operate and release for each vertical step of the shaft. They form part of the control path for the automatic vertical stepping process. Now we'll take a look at the rotary magnet. The rotary magnet is a twin coil assembly. This is the left side view of the coils. And this is the right side view. The rotary magnet is energized or magnetized each time a rotary step of the shaft is required, and it is de-energized or demagnetized after each rotary step is completed. It has an armature that is attracted to the two coils each time they are energized, and which pivots back to its released position each time the coils are de-energized. Attached to an extension arm of the armature is a rotary pawl. With each attraction of the armature to the rotary magnet, the pawl engages a tooth of the rotary ratchet and forces it to rotate clockwise by one step. With each release of the armature away from the rotary magnet, the pawl disengages from the rotary ratchet tooth. So each energizing and de-energizing of the rotary magnet steps the shaft clockwise by one rotary step. Also associated with the rotary magnet is a set of contact springs called the Rotary Interrupter springs. This spring set is operated by a rotary interrupter lever which is attached to the rotary armature. Each time the armature is attracted to the rotary magnet, the attached lever pivots and operates the rotary interrupter springs. Each time the armature returns to its released position upon de-energizing of the rotary magnet, the lever pivots back to its normal position, releasing the rotary interrupter springs. So the rotary interrupter contact springs operate and release for each rotary step of the shaft. They form part of the control path for the automatic rotary stepping process. We're going to take a look now at a couple of very odd-shaped pieces of apparatus. This first one that you're looking at now is called the stationary dog. And this second one is called the double dog. As I say, two odd-shaped pieces. I'm just not sure why they're called dogs. Here's the double dog mounted on the line finder. It is vertically mounted with its head at the bottom. It fits over a pin that acts as a hinge about which the double dog is able to pivot. The top leg of the double dog is called the vertical dog because it engages with the vertical ratchet, and the bottom leg of the double dog is called the rotary dog because it engages with the rotary ratchet. Both the vertical and the rotary dogs are held pressed against their respective ratchets by the tension of this spring which is appropriately called the double dog spring. During vertical stepping, the vertical dog leg prevents the shaft from slipping downwards between engagements of the vertical pawl. During rotary stepping, the rotary dog leg prevents the shaft from rotating backwards or anti-clockwise between engagements of the rotary pawl. When rotary stepping is finished, the rotary dog leg holds the shaft fixed in its rotary off normal position for the duration of the call. And here's the stationary dog mounted on the line finder. It is also vertically mounted, but with its head at the top. Its bottom leg provides a rest position stop for the vertical pawl. The top leg of the stationary dog engages with the vertical ratchet, but only when the shaft is in a rotary off normal position. When the shaft is in its rotary normal position, as you see here, the stationary dog's top leg resides in a channel cut into the vertical ratchet and is not in contact with the ratchet at this point. And it has no effect on the vertical stepping of the ratchet. When the shaft begins to rotate clockwise, the vertical ratchet channel rotates away from the stationary dog leg, which now engages the underside of one of the ratchet's teeth. This leg provides support for the shaft during the clockwise rotary stepping. When rotary stepping is finished, the stationary dog leg holds the shaft fixed in its vertical off normal position for the duration of the call. When a call has ended and the line finder is being released, the stationary dog leg provides vertical support for the shaft during its anti-clockwise rotation. When the shaft reaches its rotary normal position, the stationary dog again resides in the vertical ratchet channel, no longer providing support for the shaft, which is free to drop down to its vertically normal position. There is one other magnet on the line finder that we need to talk about, and that is the release magnet. The release magnet is a single coil assembly. It is energized or magnetized whenever the shaft needs to be returned to its normal released position, and it is de-energized or demagnetized when that action has been completed. This action normally occurs at the end of a telephone call, when the entire switch train is released to make the switches available for a subsequent call. It has an armature that is attracted to the coil each time the coil is energized. The armature pivots back to its released position each time the coil is de-energized. Attached to the bottom of the armature is a pin. Each time the release armature is attracted to its coil, the pin engages the head of the double dog. This causes the double dog to pivot, disengaging its legs from the vertical and rotary ratchets. This permits the shaft to rotate anti-clockwise to its rotary normal position. As I mentioned earlier, in this position, the shaft is no longer supported by the stationary dog, and so the shaft drops down to its vertically normal position. This action causes the release magnet to be de-energized, which permits its armature to pivot back to its released position. The tension of the double dog spring then forces the double dog to pivot and re-engage with the vertical and rotary ratchets. Attached to the cover plate are these 4 test jacks. The top 2 jacks are extensions of the transmission path tip and ring leads that connect the line finder to the first selector. The top jack is the ring jack, and the second jack is the tip jack. These test jacks are accessed by the CO technicians using a test set like the one shown here. This is a Western Electric number 1013A dial hand test set that was manufactured in 1969. It can be equipped with a variety of plug types. This one is presently equipped with a number 248 plug, which is designed specifically to plug into step-by-step switch test jacks. As you can see here, with the test set plugged into an idle line finder, the technician can test for dial tone or dial a call through the switch train. If a switch is in use, the tech can test for a conversation, for an off-hook telephone, or for a trouble condition. And here is a well-known CO technician about to perform a test using a Western Electric 1013A dial hand test set. The third test jack is connected to the line finder start lead. It can be used to check the vertical and rotary stepping capability of the line finder and the 11th rotary step functionality. By grounding this jack, the line finder will be seized and begin hunting for a line requesting dial tone. However, since there is no line requesting dial tone, the line finder will step up to the 10th bank level and then rotate to the 11th rotary step, release, and repeat this procedure until the ground is removed. Let's watch. The fourth test jack has no circuit connectivity. It merely provides support and spring tension for any test plug being used. Let's take a look at some of the other parts of the line finder switch that are best seen with the switch removed from its shelf mounting position. Cut into the switch base plate are these 4 bayonet-style mounting slots. These slots slide over these 4 pins on the line finder mounting shelf that firmly hold the line finder in its fixed position. This rectangular metal can contains the A network, which is a protection network. It consists of 2 1 microfarad capacitors and a 160 ohm resistor. Its function is to prevent electrical arcing across contacts 1 and 2 of the C relay, which are used to energize and de-energize the vertical and rotary stepping magnets. Located below the A network is another assembly. This assembly, which consists of these terminating pins, a wooden mounting block, and these sets of prongs, is called the line finder plug. There are 16 prongs arranged in 8 pairs, with an insulator separating each prong of a pair. The wiring on the plug's terminating pins connects to internal line finder circuitry. On the line finder shelf, there is a corresponding set of 16 jack springs arranged in 8 pairs. The 2 jack springs in each pair are separated by an insulator, and the whole assembly is insulated from the framework by a wooden mounting block. The 8 line finder plug prong pairs line up with the 8 jack spring pairs, so when the line finder is in position, each plug prong pair fits tightly between the 2 jack springs of a pair, such that there is electrical conductivity between each prong and its mated jack spring. The jack spring wiring provides the line finder with much of the connectivity it requires to external circuits, such as DC power, ground, wiring to the first selector, and wiring between line finders. The other means of connecting to external circuits is through the wipers. This electrical connectivity arrangement makes the line finder a plug-and-play device. It is easily removed and installed for maintenance purposes without any wiring to disconnect. A red-colored Make Busy switch is mounted to the bottom of the cover plate. This switch is operated when it is necessary to make the switch unavailable for service. When operated, the Make Busy switch emulates an operated D relay in that it transfers its line finder's start lead to the next line finder in the sequence selection chain and opens its line finder's branch of the open chain multiple. Now we're going to take a look at how the line finder equipment is set up in a central office. First, we'll look at how the telephone set connects to the central office equipment and where the line finder fits into the path that connects the telephone to the dial switch train. Here's a general overview diagram of the telephone set connection to the central office. There are two wires coming from the telephone set. These are designated as the tip and the ring wires. In the field, the telephone set is connected to a cable pair. At the central office, a two-wire jumper on the main distributing frame connects the cable pair to a particular line circuit. From the line circuit, the tip ring and sleeve leads are cabled to line finder bank terminals. At the intermediate distributing frame, a three-wire jumper connects the tip ring and sleeve leads to a set of connector bank terminals, which define the telephone number assigned to the telephone set. Now, I just want to point out a couple of things you need to know about in these schematic type diagrams. These rectangular boxes represent the coils of the designated relay. A dash line represents brake contacts. With the relay released, electricity flows through. With the relay operated, electricity flow is blocked. An X represents make contacts. With the relay released, electricity flow is blocked. With the relay operated, electricity flows through. And here's a switching diagram showing the path of a call through my demonstration unit from telephone set Pennsylvania 65000 to telephone set Beechwood 45789. We see the calling telephone set connected to the line finder bank terminals and the wipers connecting the bank terminals to the line finder circuitry. Now we see how the line finder fits into the dial switch train. It is permanently tied to a first selector, so there is one first selector dedicated to each line finder. The tip ring and sleeve outputs from the line finder are connected to the tip ring and sleeve inputs of the first selector. The first selector is a numeric switch that processes one or more dialed numbers. It returns dial tone to the calling telephone to indicate that it is ready for dialing to begin. The line finder is only used on originating calls. Its purpose is to set up a connection from the calling telephone to the dial switch train so that a telephone number can be dialed and a connection set up to the called telephone. The line finder can only serve one call at a time and remains connected to that call for its entire duration. Since this video is only concerned with line finder activities, we will not be following the progress of the call path setup shown in this diagram. Line finders are equipped in groups, and this is a diagram of a typical line finder group setup. To differentiate between line finder groups in a central office, each line finder group is given a number, beginning at line finder group number 1 and working upwards from there. The line equipment address of a telephone line in a step-by-step central office consists of its line finder group number and its line circuit terminal number. It was generally just called its group and terminal. This group has a capacity for up to 20 line finders. Within a group, the line finders are distributed over 2 shelves of up to 10 line finders per shelf. On the lower shelf, the line finders are numbered left to right, 1 to 10, and on the upper shelf, the line finders are numbered left to right, 11 to 20. Bolted to the bottom of each line finder is a 3-tier bank assembly, with each bank having the same number as its associated line finder. Each line finder group serves 200 line circuits, which are mounted to the right of the line finders. The line circuits are mounted in 20 rows of 10 line circuits per row. As we saw earlier, the tip ring and sleeve leads of these line circuits are cabled to line finder bank terminals. The 200 tip ring and sleeve terminations are multipled across all 20 banks so that each of the 20 line finders has, through its wipers, access to the same 200 line circuits. So the 200 tip ring and sleeve terminals on bank 1 are multipled to bank 2, which are multipled to bank 3, and so on down to bank number 10. That multiple then is carried up to the upper shelf and multipled from bank 11 to bank 20. Not all central offices were equipped with a full complement of 20 line finders per group. Line finders and their associated first selectors were expensive to provide and were engineered to meet a government regulator's specified service criterion. That criterion was that in the busy hour of the busy season, 1.5% of the calls should be delayed greater than 3 seconds. Telephone company traffic engineers projected the busy hour loads per line finder group and applied these to traffic capacity tables that predicted the amount of dial tone delay for a range of loads and quantity of line finders. It was not unusual to see only 12 to 14 line finders equipped in small town central offices. It is interesting to note that in the busy hour, in order to meet the service criterion, a line finder could only be in use for 60% of that hour and needed to be idle for the other 40%. Here's what the line finder groups look like mounted in a lineup of line finder bays in a central office. In a number 1 step-by-step office, these bays are 11.5 feet high and about 7 feet wide and can each mount 3 line finder groups. Try to imagine how much floor space was taken up by step-by-step equipment. A large 50,000 line office would have somewhere around 24,000 line finders, selectors, connectors, and miscellaneous switches. The line finders alone would require 84 of the bays shown here. The line circuit terminal numbering is defined by the location of the line circuit's terminals on line finder bank number 1. The tens digit of the line circuit terminal number is its bank level number. The units digit of the line circuit terminal number is its rotary position number. For line circuits whose tip and ring leads are assigned to the middle bank tier, a hundreds digit of 1 is added to the terminal numbering scheme. One of the objectives in the line finder group design is to reasonably equalize the level of service provided to all lines. Level of service means the amount of time it takes to be connected to dial tone. Within any one line finder, this service level is not equitable. For example, here's the bank assembly for line finder number 1. If line circuit 11 connects to line finder number 1 on a dial tone request, it only takes about 1/10 of a second to get dial tone, because the line finder shaft and wipers only have to step vertically 1 step and rotate horizontally 1 step to make the connection. However, if line circuit 00 connects to line finder number 1 on a dial tone request, it takes about a full second to get dial tone, because the line finder shaft and wipers have to step vertically 10 steps and rotate horizontally 10 steps to make the connection. However, this inequity is much reduced when all the line finders in the group are considered together as a single serving unit. We'll see how this is accomplished shortly. Another objective of the line finder group design is to minimize the amount of switch wear due to their high degree of mechanical activity. The objectives of minimizing switch wear and providing equitable service levels are accomplished mainly by 2 features of the line finder group design. One is the line finder multiple slip arrangement, and the other is the line finder selection sequence process. First, let's take a look at the line finder bank multiple slip arrangement on banks 1 to 10 on the lower shelf. Here we see the terminal assignment locations on line finder bank 1. We know that these 200 tip ring and sleeve leads are multiple to banks 2 to 10. However, the terminal assignment locations are different on each of the 10 banks. Each terminal is always assigned to the same rotary position on each bank, but on a different vertical or level position. So the multiple is slipped as it proceeds across the 10 banks. Let's look at the multipling from level 0 of line finder bank 1. Here we have terminals 01 to 00. This diagram shows the slipped multiple arrangement. Looking at line finder bank number 1, our line circuits 01 to 00 are on level 0. And then they are multipled on line finder bank 2 to level 9. And then level 8, level 7, level 6, level 5, level 4, level 3, level 2, and finally they're on level 1 on line finder bank 10. Now let's look at line circuits 11 to 10. On line finder 1, they're on level 1, and then on level 0 on bank number 2, followed by level 9, 8, 7, 6, 5, 4, 3, and 2 on bank number 10. Looking at level 1 of the lower tier across all 10 banks, we see that all 100 line circuits 00 to 99 have one appearance on level 1. With the multipling arrangement, it follows that each of these line circuits will also have one appearance on level 2 and level 3 and level 4 and so on all the way up to level 0. This multipling arrangement is exactly duplicated in the middle tier for line circuits 100 to 199, and then the whole multipling arrangement is exactly duplicated on the upper shelf for line finders 11 to 20. We'll see how this multiple slip arrangement helps to minimize switch wear and provide equitable service levels after we look at the line finder selection sequence process. There are a couple of mounting plates above the line circuits that contain the group and alarm relay circuit. This circuit has a number of functions, including controlling the line finder selection process, monitoring for trouble conditions, activating alarms, and providing line finder maintenance test equipment and access. We will focus mainly on its line finder selection process in this video. However, it's confession time, and this is a good place to make it. I lied about the number of line circuits in a line finder group. It's only 198, not 200. Line circuit bank terminals 10 and 110 do not have line circuits. These terminals are wired to the group and alarm relay circuit and are used for maintenance test procedures. However, these types of line finder groups are still always called 200 line groups. To accommodate the line finder selection process, the 200 line circuits in a line finder group are broken down into 10 subgroups of 20 line circuits each. The assignments of the line circuits to the 10 subgroups, which are numbered 1 to 10, are shown here. Notice that for each subgroup, its 20 line circuits are all on the same level, although of course the level number they are on changes across the banks as we have just seen. These subgrouping arrangements take place in the wiring and relays in the group and alarm relay circuit. It contains 10 subgroup-specific relays, designated as G1 to G10, with the G number aligning with the subgroup numbers shown here. Now let's take a look at how the Subgroup G Relays get operated. When a station initiates a dial tone request, its line relay operates. A make contact of the line relay closes the operating path for its subgroup's G relay. Here we see the make contacts of the 20 line circuits associated with subgroup 1 and the 20 line relay make contacts associated with subgroup 10. Ground is connected to one side of the make contacts and the G relay winding to the other. Notice that all 20 line relay make contacts in the subgroup are set up in parallel and connect to the winding of its subgroup's G relay. So whenever one or more of the 20 line relays in the subgroup are operated, the G relay operates. The G relay stays operated for as long as any one of the 20 line relays in its subgroup remains operated. When all 20 line relays are released, the G relay releases. What does the operated G relay do for us? Well, it does a couple of things. First, it grounds the commutator segments associated with the level on which the subgroup's line circuits are terminated. For example, here we have the bank assembly for line finder number 1. If the G1 relay is operated, it grounds commutator segment number 1. If the G5 relay is operated, it grounds commutator segment number 5. If the G9 relay is operated, it grounds commutator segment number 9. This identifies to the line finder on which bank level the line requesting service is located. This information is passed to the line finder by its commutator wiper, which brushes across the commutator segments during vertical stepping. Since the bank multiple is slipped, it is necessary to also slip the commutator multiple in a like manner, so that for any operated G relay, it grounds the correct commutator segment no matter which line finder gets selected. Notice that none of the G relays ground level 0. On any call, level 0 is always the last choice level, and so commutator segment 0 is permanently grounded with a straight multiple across all commutators. This ensures that in the event of a trouble condition, the line finder will not try to vertically step beyond level 0, and instead will stop at level 0 and begin rotation. The second thing the operated G relay does is extend ground to its subgroup start lead. The start lead connects to what is called the line finder's start transfer chain. The start ground will connect to the A relay winding of an available line finder. The A relay winding has battery on its other side, and so the A relay operates when connected to the grounded start lead. In the diagram, assume subgroup relay G1 is operated, and ground is extended through the make contacts to the start 1 lead, to its first choice line finder, which is line finder number 1. The start ground is extended to this line finder's A relay winding, which closes its operating path. The line finder is seized by the operation of the A relay, and it proceeds to connect the calling station to a dial tone from a first selector. Now let's see what happens when a line finder is not available for selection. When a line finder is not available for selection, its D relay is operated. From the diagram, we can see that if a D relay is operated, its A relay operating path is opened by a break contact of the D relay, and so the A relay cannot operate and the line finder cannot be seized. Instead, a make contact of the operated D relay extends the ground on the ST lead through to the next choice line finder in the start chain. The line finder's start chain, or selection sequence chain, is a continuous unidirectional loop. In this diagram, we show a loop or circle of 20 line finders. The selection sequence proceeds clockwise around the circle, always in this exact order. The diagram also shows the entry point or starting selection point of each subgroup of 20 lines. Notice that each subgroup has a different entry point. Subgroup 1 is represented by the G1 box. G1 refers to G relay number 1 in the group and alarm relay circuit, which is associated with line circuits numbered 11 to 10 and 111 to 110. Subgroup 2 is represented by the G2 box. G2 refers to G relay number 2 in the group and alarm relay circuit, which is associated with the 20 line circuits numbered 21 to 20 and 121 to 120, and so on through to G10, which is associated with the 20 line circuits numbered 01 to 00 and 101 to 100. Let's look at the selection process using subgroup G1 as the subgroup requesting service. The entry point for subgroup G1 is line finder number 1. If line finder number 1 is available for selection, its D relay is released, and so its A relay will operate to seize the line finder. If line finder number 1 is unavailable for service, its D relay is operated, and the start 1 start lead ground is extended to the second choice line finder in the chain, which is line finder number 11. If line finder number 11 is available for selection, its D relay is released, and so its A relay will operate to seize the line finder. If line finder number 11 is unavailable for service, its D relay is operated, and the start 1 start lead ground is extended to the third choice line finder, which is line finder number 10. This transfer pattern continues sequentially clockwise around the loop until the first available line finder is seized. If there are no available line finders, the call will be delayed instead of cut off or blocked, and will eventually be served when a line finder becomes available. Customers were advised to wait for dial tone through instructions in the telephone directory, advertisements, or even a message on the dial. Dialing before receiving dial tone meant that one or more of the dial pulses were not received by the first selector. This resulted in getting a wrong number, or a no-ring condition, or reaching a vacant level tone or vacant level announcement. So here's how the multiple slip and the selection process achieve the objectives mentioned earlier. The distribution of the start selection points for each subgroup of 20 lines tends to even out the usage across all line finders. This helps to achieve the objective of distributing the wear across all the line finders. Here's a diagram that shows the line finder selection sequence that we've been discussing, but in a table format. Let's look at the subgroup 1 selection process. The first and second choice line finders are line finders 1 and 11. Notice that on these two line finders, the 20 lines in subgroup 1 appear on level 1. The third and fourth choice line finders for subgroup 1 are line finders 10 and 20. Notice that on these two line finders, the 20 lines in subgroup 1 appear on level 2. For choices 5 and 6, the lines appear on level 3. This selection pattern continues, increasing the level number by 1 per two sequential choices, until the last two choices are reached and the lines appear on level 0. With this pattern, the line finder selected will always be one in which the line requiring service appears on the lowest level of all of the line finders available for selection. This minimizes the time taken to get connected to dial tone and reduces wear on the line finder switches by minimizing the amount of vertical stepping required. So the combination of the multiple slip and the selection process has achieved the objectives of distributing wear and tear fairly evenly across all the line finders and given reasonably equitable speed of dial tone to all lines. However, one problem with the selection process is the uneven distribution between the selection of the lower shelf and upper shelf line finders. Notice that the first choice line finders for all subgroups is a line finder on the lower shelf, that is, any of line finders 1 to 10, while the line finders on the upper shelf, line finders 11 to 20, are always second choice. This lower shelf line finder preference arrangement applies all along the selection chain. This results in higher usage on the lower shelf line finders versus the upper shelf line finders. An enhancement to the selection process was introduced in the mid-1950s to correct this problem. A modification was made to the group and alarm relay circuit that doubled the number of start leads from 10 to 20 by giving each subgroup 2 start leads, one for a line finder on the lower shelf and the other for a line finder on the upper shelf. Which one of the 2 start leads to be used was alternated on each call by flip-flop circuitry in the group and alarm relay circuit. The flip-flop involved a Z relay that was alternately operated on one call and released on the next. When released, a line finder on the lower shelf was first choice. When operated, a line finder on the upper shelf was first choice. Now we're going to have a look at the transfer start path and the role of the D relay in maintaining the continuity of that path. The continuity of the start transfer path is maintained by make contact of the D relay. The D relay of all in-use line finders remains operated for the duration of a call, and so the transfer path through all in-use line finders is maintained. When a line finder releases, the primary winding of the D relay is de-energized, and the D relay can release, unless there is ground on its transfer path start lead. Ground on an incoming start lead to this line finder would indicate that there is another dial tone request in progress using a different line finder, but that request is using this line finder's transfer path to establish its dial tone connection. We know that that dial tone request has not yet been completed, because only a request in progress has a grounded start lead. That ground is removed when the line relay and the subgroup G relay release. If this line finder's D relay release now, it would open the transfer path and thereby disrupt the call in progress, causing that call's seized line finder to release. To prevent this disruption, this line finder's D relay remains operated over its secondary winding until there is no ground on its transfer path start lead and it can release. When telephone traffic gets very busy, all 20 line finders in a group can be in use simultaneously, and a queue of delayed dial tone requests forms. But as calls end and line finders release, their D relays remain locked operated over their secondary windings, because there is a queue of grounded start leads through operated G relays of subgroups with lines waiting for service, and so the released line finders are not available for selection. The group and alarm relay circuit takes care of this situation by releasing all the D relays in idle line finders. This is accomplished by what is known as the open chain multiple circuitry. The open chain multiple is a circuit path that has a break contact of all 20 D relays wired in parallel. If at least one D relay is released, the path is closed. If all 20 D relays are operated, the path is open, and the S and CH relays in the group and alarm relay circuit release. With the S and CH relays released, the OB relay in the group and alarm relay circuit now operates. The operated OB relay removes ground from all start leads, releasing all D relays locked operated over their secondary windings in idle line finders, thus making these line finders once again available for selection. The released D relays closes the open chain multiple, reoperating the S and CH relays. CH and S operated releases the OB relay. The released OB relay permits ground to be applied to all start leads of operated G relays, allowing waiting dial tone requests to be served. My step-by-step demonstration unit only has one line finder, so I have no actual equipment to demonstrate line finder preference selection processes or subgroup operations, so I will do this using diagrams. For the purposes of this video, we are going to assume that I have a line finder group equipped with 20 line finders. My demonstration unit line finder will be line finder number 1 in this group. I am going to originate a call from telephone set Pennsylvania 65000. It is assigned to line circuit terminal 00 in the line finder group. The bank assembly for line finder number 1, which is the line finder we are using in this example, has the line circuit terminals assigned as shown in this diagram. The line circuit we are using is terminal 00. Its tip and ring leads are on the 10th rotary position of the 10th level of the lower bank tier, and its sleeve lead is on the 10th rotary position of the 10th level of the upper bank tier. When I lift my handset off the telephone set base, the switch hooks pop up and close the loop through the telephone set. This operates the line relay in the line circuit. Line circuit terminal number 00 is associated with subgroup number 10, which is relay G10 in the group and alarm relay circuit. Operated line relay 00 closes the operating path for relay G10, which now operates. The operated G10 relay grounds start lead number 10, which initiates the hunt for an idle line finder. Start lead number 10 enters the hunt for an idle line finder at line finder number 10, which is the first choice line finder for the subgroup G10 line circuits. If a line finder is available for selection, its D relay is in its released position. and any grounded ST lead will seize its earliest choice line finder by operating that line finder's A relay. If a line finder is unavailable for selection, its D relay is operated, and any grounded ST lead will be transferred past that line finder to its next choice line finder. In our example, line finder number 10 is in use on another call, and so its D relay is operated. So the ST10 start lead is transferred to line finder number 20, which is the second choice line finder for that subgroup. It is also in use, and the start lead is transferred again to line finder number 9, which is the third choice line finder. Just so happens in our example that all the line finders from number 10 through to line finder number 12 in the selection sequence chain are in use with their D relays operated, transferring the grounded start lead ST10 as far as line finder number 1, its 19th choice line finder. The grounded ST10 lead operates the A relay in line finder number 1. The operated A relay provides operating and holding ground paths for other relays and magnets in the line finder, and remains steadily operated until the connection to the first selector has been established, at which time it releases for the duration of the call. The C relay is operated via its secondary winding by the operated A relay. The C relay controls the vertical and rotary stepping functions. It quickly operates and releases via its secondary winding to energize and de-energize the vertical magnets and the rotary magnets to accomplish vertical and rotary stepping. When the connection to the first selector has been established, the C relay releases and remains released for the duration of the call. With both the A and C relays operated, the energizing path for the vertical magnet is closed, and so the vertical armature operates. The vertical pawl engages the vertical ratchet and steps the shaft and all of its attached apparatus vertically upwards by one step. All three sets of horizontal wipers step up one position so that they are in line with level 1 of all three bank tiers. In addition, the vertical commutator wiper steps up one position so that it is in contact with the level 1 commutator segment. The first vertical step of the shaft also raises the normal pin away from the off-normal finger, allowing the vertical off-normal or VON springs to operate. When the vertical armature operates, its arm pushes upwards against the L-shaped vertical lever, which pivots and opens the contact springs of the vertical interrupter. This opens the operating path of the C relay, which releases. The release of the C relay de-energizes the vertical magnet, and so its armature releases. The vertical interrupter springs reclose. And the vertical pawl disengages from the vertical ratchet. If the commutator segment on which the commutator wiper rests is not grounded, then this level does not contain the bank terminals of the line requesting service, and more vertical stepping will be necessary. In our example, the line circuit terminal is on the 10th level of the bank assembly, and so there is no ground present on commutator segments 1 through 9. This vertical stepping cycle will be repeated for levels 2 through 9. Let's look at the level 2 stepping cycle. The C relay reoperates. The vertical magnets are re-energized and the vertical armature operates. The vertical pawl engages the vertical ratchet and steps the shaft up by one step. The horizontal wipers step up to the second level, and the commutator wiper steps up to the second commutator segment. The vertical lever pivots, opening the vertical interrupter contact springs. The C relay releases. The vertical armature releases. The vertical pawl disengages from the vertical ratchet. The vertical interrupter springs reclose. This ends the vertical stepping cycle for level 2. Let's just watch and listen to the level 3 stepping cycle. Okay, now we'll skip past the repetitive vertical stepping cycles for levels 4 through 9. We will resume with the horizontal wipers resting at the 9th level, and we are ready to begin the vertical stepping cycle for the 10th level. Let's watch. Everything up to this point is the same as the other vertical stepping cycles. However, now the commutator wiper is resting on the 10th commutator segment, which corresponds to the level on which our line circuit, terminal 00, is located on the bank assembly. This commutator segment is grounded. It actually has a permanent ground on it since it is at the highest level and acts as a failsafe to prevent further attempts at vertical stepping. Here's a diagram of the commutator wiring multiple. We're on bank assembly 1. You can see that the 10th level is permanently grounded, as are the 10th levels of all 20 bank assemblies in the line finder group. This commutator ground completes the operating path for the E relay, which now operates. This same path holds the C relay operated momentarily to prevent further vertical stepping and to allow time for the E relay to operate and shift the stepping operation from vertical to rotary. The E relay is slow to operate to ensure that the wipers have stopped vibrating and won't snag before rotary stepping begins. The slow operating feature is accomplished by the use of this copper slug at the armature end of the winding spool. The copper slug enables the application of Lenz's law. When the E relay winding is energized, a magnetic field begins to grow around its coil. The changing strength of this field induces a magnetic field around the copper slug, such that its polarity opposes the polarity of the field around the relay coil, slowing down the rate of its increasing flux, thus delaying the relay operation. E operated transfers the stepping activity from vertical to rotary and de-energizes the vertical magnet. E locks operated via its secondary winding and its own make contacts. This is necessary since its primary winding operating path becomes ineffective as soon as rotary stepping begins. The E relay remains steadily operated until after cut-through of the calling line to the first selector has been completed, at which time it releases. E remains released for the duration of the call. When E operates, the vertical armature releases. The vertical pawl disengages from the vertical ratchet. The vertical interrupter springs reclose. E operated also closes the energizing path for the rotary magnet, and so the rotary armature operates. Attached to the rotary armature is the rotary pawl, which now engages the rotary ratchet and steps the shaft and all of its attached apparatus horizontally clockwise by one step. This steps all 3 sets of horizontal wipers into contact with the first rotary position terminals on the 10th level. The rotary interrupter arm, attached to the rotary armature, operates, closing make contacts 3 and 4 and opening break contacts 1 and 2. This opens the operating path of the C relay, which now releases. The release of the C relay de-energizes the rotary magnet, and so the rotary armature releases. And the rotary pawl disengages from the rotary ratchet. The rotary interrupter arm releases, reclosing break contacts 1 and 2 and opening make contacts 3 and 4. If neither of the upper or lower sleeve terminals on which the sleeve wipers are resting has negative 48-volt battery from the CO relay winding in the line circuit, then these terminals are not the bank terminals of the line requesting service. In this case, more rotary stepping is necessary. In our example, the line requesting service is on the 10th rotary position, and so there is no battery present on terminals 1 through 9. The rotary stepping cycle will be repeated for rotary positions 2 through 9. Let's look at the rotary position 2 stepping cycle. With the release of the rotary armature, the path for operating the C relay is closed, and so the C relay reoperates. This energizes the rotary magnets, and so the rotary armature operates. The rotary pawl engages the rotary ratchet, and the shaft is rotated clockwise by 1 step. The horizontal wipers rotate with the shaft and will come to rest on the second set of rotary position terminals. The rotary interrupter arm operates, closing make contacts 3 and 4 and opening break contacts 1 and 2. This releases the C relay. With C released, the rotary magnets are de-energized, and so the rotary armature releases. And the rotary pawl disengages from the rotary ratchet. The rotary interrupter arm releases, reclosing break contacts 1 and 2 and opening make contacts 3 and 4. This ends the rotary stepping cycle for rotary position 2. Let's just watch and listen to the rotary position 3 stepping cycle. Okay, now we will skip past the repetitive rotary stepping cycles for rotary positions 4 through 9. We will resume with the horizontal wipers resting on rotary position 9. We are ready for the next rotary stepping cycle to begin, which will be the last rotary step to rotary position 0. Let's watch. Up to this point, the activity on this rotary stepping cycle has been the same as on the previous cycles. However, now the lower sleeve wiper is resting on the sleeve terminal of line circuit 00, which is the line requesting dial tone. As we can see from this diagram, there is battery on the calling line sleeve terminal that originates on the far side of the line circuit's CO relay winding, through the operated make contacts of the line relay and to the sleeve bank terminal. The connection of this battery through the sleeve wiper into the line finder switch closes the operating path for both the CO relay in the line circuit and the F relay in the line finder. The initial operating path for the F relay is through its primary and tertiary windings. The effective flux created by the current through these windings is sufficient to permit the operation of early make contacts 1 and 2, but is not sufficient to overcome the combined tension created by these ganged contact springs. Operated contacts 1 and 2 complete an energizing path to the F relay's secondary winding. The much higher flux through the secondary winding which has over twice as many turns as the primary winding and a slightly higher operating current, allows the F relay to fully operate. The F relay is held operated via its secondary winding for the duration of the call. In the line circuit, the CO relay winding is energized over the same sleeve lead path as the F relay's primary winding. The CO relay operates and locks over its own make contacts. Break contacts of the CO relay release the line relay. The sleeve ground holding the CO relay operated is also passed over the sleeve lead to the connector bank terminal for the calling line's telephone number. This makes this line appear busy to incoming calls. The release of the line relay discontinues the calling line's request for a line finder. If there are no other lines in the same subgroup requesting service at this point in time, the G10 relay in the group and alarm relay circuit will release. The release of the G10 relay removes ground from the ST10 start lead, which will initiate de-energizing of the A relay winding in the line finder. The fully operated F relay holds the C relay operated momentarily to prevent further rotary stepping. It also closes the tip and ring transmission path between the calling station and the first selector. The first selector returns dial tone to the calling station. The loop through the calling telephone set operates the A relay in the first selector, which is quickly followed by the operation of the B relay. The operated B relay grounds the sleeve lead back to the line finder. This provides the holding ground that maintains the line finder switch in its connected state. When dialing begins, continuity of this holding sleeve ground is maintained by succeeding switches in the dial train. Back in the line finder, the operated F relay closes the operating path for the D relay via its primary winding. The operated D relay performs a number of tasks. The D relay closes a direct path between the grounded sleeve lead from the first selector and the sleeve lead to the CO relay in the line circuit. This path keeps the CO relay operated for the duration of the call. The D relay closes a path between the grounded sleeve lead from the first selector and the secondary winding of the F relay. This path keeps the F relay held operated for the duration of the call. The operated D relay cuts off the operating path for the A relay and transfers the start chain path from this line finder's A relay to the succeeding line finder in the chain. While operated, the A relay provides the initial ground on the sleeve lead to operate and hold the CO relay in the line circuit. The A relay is slow to release to ensure that this holding ground is maintained long enough for the replacement ground path from the first selector to be applied. The slow release feature is accomplished through the use of this large copper slug mounted at the heel end of the relay spool. This enables the application of Lenz's law. When the A relay winding is de-energized, it causes the magnetic field around its coil to begin collapsing. This collapsing field induces a magnetic field around the copper slug, such that its polarity strengthens the field around the relay coil, slowing down the rate of its decreasing flux, thus delaying the relay's release. If the A relay winding was de-energized by the earlier release of the G10 subgroup relay, the A relay will now finish its slow release process. If the A relay was de-energized by the operation of the D relay, it will now begin its slow release process. In either case, the net result is that the A relay releases. The operated D relay partially closes a holding path for itself via its secondary winding. Ground on any start lead that reaches this line finder will keep the D relay operated even if the line finder releases. The operated D relay opens line finder number 1's branch of the open chain multiple. The operated D relay releases the C relay and the E relay. The released E relay de-energizes the rotary magnet, which releases the rotary armature. This disengages the rotary pawl from the rotary ratchet. And the rotary interrupter lever releases, returning the interrupter springs to their normal released position. The line finder is now in its connected stage. The D and F relays are operated, the vertical off normal springs are operated, the shaft and wipers are held in a fixed off normal position by the spring tension of the double dog. The tip ring and sleeve wipers are connected to the bank terminals of the calling line. The calling line is cut through to the first selector. The line finder remains in this static state until it is released. At the end of the call, when the calling station hangs up, the loop through the calling telephone is opened, which triggers the release of the entire switch train. When the sleeve ground coming from the first selector is removed, the F relay releases, and the CO relay in the line circuit also releases, making the calling line appear idle to incoming calls. The release of the F relay closes the energizing path for the release magnet, causing its armature to operate. The pin of the armature strikes the head of the double dog, causing the double dog to pivot and disengage from the teeth of the ratchets. The tension shaft spring now forces the shaft and all of its attached apparatus to rotate anti-clockwise to the rotary normal position. With the leg of the stationary dog now residing in the vertical ratchet channel, there is no vertical support for the shaft, and so it and all of its attached apparatus drops down to its vertically normal position. As the shaft nears the end of its vertical drop, the normal pin strikes the off-normal finger, causing it to pivot to its rest position, which releases the vertical off-normal springs. The release of the VON springs de-energizes the release magnet, and so its armature releases, permitting the double dog to re-engage with the vertical and rotary ratchet teeth. The release of the VON springs de-energizes the primary winding of the D relay. If the secondary winding of the D relay is not energized, the D relay releases. The line finder is now idle and is available to serve new dial tone requests. If the secondary winding of the D relay is energized, it means that the start chain path through this line finder is grounded, indicating that there is a dial tone request currently being processed by another line finder, or that there is a queue of dial tone requests waiting to be served. This line finder is considered to be idle, but is unavailable to serve new dial tone requests until the D relay releases. The D relay releases under two conditions. First, if the start chain ground is removed because all active dial tone requests have been served. Or second, when the open chain multiple circuitry in the group and alarm relay circuit triggers the de-energizing of all D relay secondary windings in the line finder group. This only occurs when all 20 D relays in the line finder group are operated. And this is what the release of the switch train, including the line finder, looks like at normal speed. Now we're going to briefly look at the differences that occur on a call that requires the use of the B relay. So let's assume that all conditions are exactly the same as in the first scenario, except that our originating line circuit will be terminal 100 instead of terminal 00. Once again, we will be using line finder number 1 and bank number 1. Our line circuit's transmission path terminals are on the middle bank on the 10th rotary position of the 10th level. On the middle bank, the transmission path terminals and wipers are referred to as T1 and R1 instead of T and R as they are on the lower bank. On the upper bank tier, the sleeve terminal of line circuit 100 is on the top side of the 10th rotary position of the 10th level. The top side sleeve wipers and terminals are called the S1 wipers and terminals, while the bottom side wipers and terminals are called the S wipers and terminals. So on this call, we will be utilizing the T1, R1, and S1 wipers and terminals. Every action on this dial tone request will be exactly the same as it was on the call from line circuit 00, up to the point where the wipers come to rest on the 10th rotary position of the 10th level. In the middle bank tier, the T1 and R1 wipers are connected to the T1 and R1 terminals of line circuit 100. In the upper bank tier, the S1 wiper is connected to the S1 terminal of line circuit 100. Battery is present on this terminal coming from the CO relay winding of the line circuit. This battery closes the operating path for the B relay. The B relay is essentially a duplicate of the F relay and operates in exactly the same manner. That is, it partially operates via its primary and tertiary windings and then fully operates via its secondary winding. The B relay is held operated via its secondary winding for the duration of the call. B operated transfers the connectivity of the transmission path wipers through the line finder from the lower bank tier tip and ring wipers to the middle bank tier tip 1 and ring 1 wipers. It also closes the operating path for the full and direct operation of the F relay via the F relay's secondary winding. The operated B relay also holds the C relay operated momentarily to prevent further rotary stepping. The remainder of the line finder activity for this call is the same as for the call from line circuit 00, except that at the end of the call, the B relay releases when the VON springs release. Now let's take a look at the 11th rotary step operation. Here we're going to see the line finder vertically step and then rotary step as on any normal dial tone request. However, after it reaches the 10th rotary position, it still hasn't detected battery on any of the sleeve terminals, so the F or B and F relays don't operate to stop rotary stepping. Line finder rotary steps one more time to the 11th rotary position. The lack of battery on any sleeve terminal can be caused by a trouble condition, an abandoned call, or a CO technician performing line finder tests. The rotary step to the 11th position occurs in the same way as any other rotary step, up to and including the release of the C relay. However, as the 11th rotary step occurs, the cam on the line finder shaft strikes the 11th rotary step contact spring assembly, causing these springs to operate. This fully operates the F relay directly via its secondary winding. F operated operates relay D via its primary winding. The operated D relay releases relays A, E, and F. This in turn de-energizes the rotary magnet, causing its armature to release. The line finder now releases in the same manner as on a normal call. If there is ground on the start lead due to a central office test procedure or a false ground condition, the D relay will remain operated and the 11th rotary step operation will be repeated on the next available line finder. If there is no ground on the start lead, the D relay releases and the idle line finder becomes available for selection. Well, this brings an end to my step-by-step line finder video. Anyone still watching must have a very keen interest in the subject, so I hope the video met your expectations. If you have any questions, please enter them in the YouTube comments, and I will certainly attempt to answer them. Thanks for watching.